And so the theme in this mini tutorial is under the test and evaluation methods for emerging technology and domains. And our two speakers are both from the SAS Institute. Joseph Morgan is actually going to go first. It's listed in reverse in the agenda. So he's giving part one. But Joseph is a principal research statistician developer in the JUMP division of the SAS Institute, where he implements features for the design of experiments platforms in JUMP. His research interests include combinatorial testing, empirical software engineering, and algebraic design theory. And so we'll be taking a break after Joseph's talk, just a short one, and then Brian Lekovitz will come back and do part two. So go ahead, Joseph.
Okay, thank you, Tom, and thanks to everyone for attending. We have a lot to get through in this first part of the tutorial, so let me get right to it. So I'd like to start by posing a question, and the question really is a fundamental and a basic question. Well, what is testing? But before digging into this question, let me just comment on the title of the slide, which is Testing Complex Engineered Systems. For this first part of the presentation and the second part, we'll focus on software systems. Software systems are an example of complex engineered systems, but I'll just point out that everything that we say here could be applied to any type of complex engineered system. So although you'll see the title Complex Engineered Systems throughout, we will be giving examples that are really focused on one type of complex engineered system. So let's get back to the question, what is testing? Well, a nice answer to this question was presented by Glenford Myers in his textbook that appeared in the late 70s called The Art of Software Testing. And it is one of the most often quoted statements that you will find in software engineering. And it's simply this: testing is a process of executing a system with the intent of finding errors. So notice what Myers is saying here, that the intent is to find errors. That is the objective, that is a goal. If someone is exercising software and the intent is not to find errors, then they're simply not testing, is what Glenford Myers would argue. So let us move on to another little point that I'd like to make here. And for the sake of consistency of terminology, I like to rephrase what Glenford Myers says to say the intent of finding faults. Nowadays, it is more common for people to use the term fault to refer to what Glenford Myers was referring to as errors, or what some people refer to as bugs. And we'll use the word faults mostly throughout this presentation. Another question then is, if the intent is to find errors, then where are these things, right? Where are the bugs, or where are the errors? And I turn to another iconic figure in software engineering, Boris Weiser, who in the early 80s wrote a textbook called Software Testing Techniques. And this quote is also one of the most widely quoted sentences from his book, where he provides this remarkable insight. Profound, but simple. Bugs lurk in corners and congregate at boundaries. Now, again, for the sake of consistency of terminology, I'll rephrase the quote: faults lurk in corners and congregate at boundaries. And let's peel this back a little bit. Focusing on congregated boundaries, what did Boris Weiser mean by this? Well, if you've been around test engineers, if you're test engineers yourselves, you have often probably heard them say, well, we are looking for edge cases. Well, that's exactly what Boris Weiser was alluding to here, that faults in software tended to show up around what are known as edge cases. You think of a piece of software presented with a certain input. There's a threshold value beyond which the software behaves in a certain way, differently on either side of that threshold. And that's what a boundary is, or an edge case. But what I really want to focus on, and what is really at the heart of today's talk, this tutorial, is the first part of Boris Weiser's quote. And it is the part where he says, faults lurk in corners. So what did Boris Beiser mean by this? What is this insight that he's providing? Again, test engineers intuitively understand this. It is often the case that faults occur at the interaction of two or more inputs. And by interaction, what I mean is if you think of a software system, and it's not uncommon for a fault to be discovered with a particular setting of one input and a different setting of another input or several other inputs. That is where the software performs in an unexpected fashion. And that is what Boris Beiser meant about faults lurking in corners. So with that said, with that as a backdrop, what this brings me to is the challenge that test engineers face, right? So it turns out that test engineers are faced with, in the process of executing software to find errors, they're actually faced with a daunting task, a formidable challenge, what I refer to as the testing challenge. And I contend, I would submit that that challenge is a multidimensional challenge. And what I'd like to showcase are three dimensions of that challenge that I think are perhaps the most important dimensions. And I'll begin with this first dimension that I characterize as the selection problem. So think of what any test engineer is faced with. They are faced with selecting test cases from the input space of a software system. And since they are imposed on their testing program is a budget, all test engineers are faced with a budget. They don't have unlimited time or unlimited money. They want to ensure that the test cases that they select from the input space, right, have the best chance of finding faults. They want to maximize the probability that they find the faults. And that is the selection problem. You can think actually of selecting test cases as sample size selection problem. And so that is one dimension of the software testing or the testing challenge. Another dimension of the challenge is what I characterize as a quality problem. And this problem is one that test engineers face all too often. The moment the testing process begins, there is someone asking, is it time for us to ship the software yet? Is it fit for use? And so that is what I contend is the quality problem. Can the test engineer make informed assertions about fitness for use as testing unfolds? That's another dimension of the testing challenge. The third dimension of the testing challenge, and some test engineers in some settings would claim that this is the most daunting one, is how do you determine, given a test case, what the expected behavior for that test case is? And I characterize this as an oracle problem, right? Now, in some instances, determining what expected behavior is straightforward. As it turns out, in many instances, it's actually a quite challenging and daunting task indeed. And so the test engineer must begin the process of testing by determining for each test case what the expected behavior is. Because if the test engineer does not know what expected behavior is, there's no way that the test engineer can know whether or not the test case was a success or a failure. I faced with this question often, actually, when I speak to test engineers and I ask them, well, what was the expected result for this test case? And if there is uncertainty, then perhaps the test engineer is playing around and not really testing. So determining expected behavior is an incredibly important problem that has to be addressed in order for you to know that what you have discovered is in fact a fault. So faults precipitate failures. Test cases are necessary to identify faults, and the identification of a fault is a precipitation of a failure. So those are two terms you'll hear me use, the word fault and the word failure. Okay. So hopefully I've convinced you that the testing burden is a daunting task. in that there is, it is an enormous test challenge. And so given the enormity of the testing challenge, how can we possibly proceed? Well, it's not surprising that I am going to claim in this tutorial that one way of approaching this problem is to apply a systematic way of not only identifying test cases, but of having the tools necessary to determine whether or not the software is fit for use. And the approach that I'm proposing here is the approach that we're going to term combinatorial testing. There are many approaches, but this is one that we're going to discuss today. So what then is combinatorial testing? It turns out that combinatorial testing is really just a family of test case selection strategies, a family of test case selection strategies used to test complex engineered systems. Now, again, I should point out that we're assuming here that these systems are deterministic. And so that's why my claim is that regardless of whether it's a software system and some other type of complex engineered system, as long as it's deterministic, we can apply these methods. So let's dig into this a little bit. What I have here is a claim that the underlying mechanism that combinatorial testing is based on is what's known as a T-covering array. The key T-covering array is a mathematical construct. We're going to get into this in some detail in a few minutes, but let me just highlight a few things here. Notice that I've underlined the part of this sentence which says that the T-covering array ensures that all possible combinations of values for some subset T of inputs appear in the derived test suite at least once. And that part of the sentence underlined aligns perfectly with what Boris Beiser was alluding to when he said faults lurk in corners. It is this connection between Boris Beiser's insight and the combinatorial testing method that provides the utility of combinatorial testing as a methodology for testing complex engineered systems. And this is what we're going to dig into in some detail. So the underlying mechanism is a mathematical construct known as a covering array. It has this wonderful property known as a covering property where all possible combinations of values exist. That aligns with what Boris Beiser said you need to focus on if you want to find where the faults are. So let's dig into this mathematical construct a little bit. But before I do that, let me just point out that combinatorial testing, I claim, partly addresses a testing challenge. It addresses a selection problem because it's a mechanism by which you select test cases. And we will see as we go on that it actually is a mechanism that allows you to select test cases that maximizes the probability of finding faults, and it actually minimizes cost. It also provides you with a mechanism. We will discover this as we go on. We will mention a few metrics, and these metrics provide you with a mechanism to address the quality problem, to allow you to determine the fitness for use of the software testing, to determine whether or not you are confident that it is reasonable to release such software into the field. It doesn't address an Oracle problem at all. The Oracle problem is still a daunting and a separate challenge that stands on its own. There could be an entire tutorial on that topic. Now, I should mention that I'm not the only one that believes that. Ryan is not the only one who believes this. There are a number of people who believe this. I'll just mention briefly a paper that Alessandra Orso and Greg Rothermel wrote. They were invited to present at a conference, Future of Software Engineering, where they were asked to write about software testing and how software testing had matured between 2000 and 2014. Now, Greg Rothermel teaches in software engineering at NC State. Alessandra Orso, for those who may not know these names, is a software engineering professor at Georgia Institute of Technology. I don't know Greg, but I know Alessandra. When he was starting his career in the Midwest, I was a junior faculty member. We wound up at the same conferences. I've followed his work. He's become a star in the software engineering research field. And so it didn't surprise me the approach that he took. Rather than just writing about what he thought was important, Alessandro and Greg made contact with 50 of their colleagues and presented them with the two questions you see there. What are the most significant contributions to testing, and what you think are the open challenges and opportunities? And they got 30 responses. And I took this nice graphic from a presentation that Alessandro did, and this sort of summarizes their findings. So I want to sort of direct your attention to just one of these. On the research contributions in the box called testing strategies, notice that combinatorial testing shows up. So combinatorial testing is an important, significant advance in the field of testing. Is one that there is some consensus amongst software engineering scholars that this is one of the most important contributions since 2000. You'll also notice if you look on the challenges and opportunities that Oracle shows up there. So the Oracle problem is also a big challenge that remains. Okay, time for covering arrays. It's an introduction. We'll dig into the mathematics of this a little bit. We won't get into all the details, but just enough for you to have an idea of what we are talking about here. So what is a covering array? It's a very, very simple idea, actually. There's some notation here that will become apparent as I walk through this. It's just an n by m array. And it's an n by m array where the ith column contains v sub I distinct symbols. These symbols could be anything. They could be numbers. They could be names. They could be whatever you may think of as a symbol. But the array has a very important property. And that property is that if you take any t columns of the array, what I refer to as a t column projection, then all possible combinations of the symbols exist at least lambda times. And if that is the case, then the n by m array is said to be a covering array. And it is that fact, that property, that provides the term covering that makes the array a covering array, a t covering array. So it's a very simple definition. There is some notational details there that I won't get into. There are a few other definitional things that I'll touch on briefly. There is this notion of a covering array number. And from that definition there, you can see it's just the minimum size, right, of a covering array. You can construct covering arrays of different sizes, and the covering array number is the smallest of them. And I provide you with a table here for you to get some insight into how the size n of a covering array changes as a number of columns increases. So as you can see here, what we have is what is known as a binary covering array, binary strength 2 covering array. And you can see that if you were to construct such an array with 15 columns, then you could do it in it would have 7 rows. And then remarkably, if you were to go up to 1,500 columns, then the number of rows barely doubles. Okay, a few notes for the statisticians in the group. If the definition sounded familiar, you would be right. It's very similar to orthogonal array, except orthogonal array has this notion of balance. Rather than the combinations existing at least lambda times, they exist exactly lambda times. And sometimes we drop the lambda because oftentimes lambda is equal to 1. Okay, some examples that I'll go through quickly. Here on the screen, we have 2 covering arrays. The one on the left is a strength 2 covering array. The one on the right is a strength 3. How do you know that? The second argument on the left is 2. The second argument on the right is 3. And we know that they are covering by just examination. So here I've identified column 1 and column 3. And if you scan through it, you will see that all combinations of the 4 symbols exist at least once. And we could examine any 2 column projections. There are 10 of them, and you would see the same property. Similarly, we could do that for the strength 3 array. In this instance, because we are talking about 3 column projections, there are 2 symbols for each column. There are 8 possible combinations, and we could continue examining the 5 choose 3 three-column projections, and you would see that they all exist. So it's a simple idea, very simple mathematical construct. Quick note, the covering array on the left is optimal, the one on the right is not. And we know this because of work that discrete mathematicians have done. So I present the suboptimal covering array, strength 3 covering array, just so that you know that it's still a covering array, even though you could construct it in fewer rows. Now, covering arrays are not always homogeneous. In this example, you will see that the first 2 columns have 3 symbols. Some people refer to this as a mixed level covering array. They're still covering arrays. You will sometimes see that the prefix of the specification has MCA rather than CA. I don't bother with that extra notation. And the same thing applies here. If you take any 2-column projection, since it's strength 2, then all possible combinations exist at least once. And this is optimal. We know this because if you look at the first 2 columns, since they both contain 3 symbols, the covering array cannot have fewer than 9 rows. Okay. And if you're curious, you can construct the covering array where the first 2 columns or 2 columns contain 3 symbols, and the remainder have 2 symbols, you up to 20 in the same number of runs. I discovered that by using a search algorithm. So by the way, I should point out that if you were to move those columns that have more than 2 symbols around, it wouldn't change anything. I just put them first because it's easier for you to notice that there are 2 columns with 3 symbols and the remainder have 2. Okay, so how about some metrics? How do you evaluate these things? Well, perhaps one of the most widely used, easiest to understand metrics is a so-called T-coverage metric proposed by Colin Mallows and his colleagues when they were at Bell Labs. They wrote a paper in 1998 that appeared in Technometrics that I think is one of the most important papers in combinatorial testing, where Colin Mallows and his colleague Dalal proposed coverage, which is a simple way of evaluating covering arrays. Rather than going through what this is, I'll just put it in words. It's just a ratio of the number of distinct t-tuples for any projection to the number of possible t-tuples. That's all it is. And we'll look at some examples. And if you want a more comprehensive treatment, Rick Kuhn at NIST wrote a paper in 2013 that does a really nice job. So let's look at some examples. We're going to go back to our strength 2 binary covering array, and we will just look at some t-coverage statistics here. So obviously when t is 2, since it's a covering array, the coverage is 100%. So that's not what is interesting here. It's interesting, though, to look at this example and say, well, what is the 3 coverage? If I were to take 3-column projections, what proportion of those the possible symbol combinations exist? It turns out that when you examine this, 70% of the combinations, when you take any 3 columns, exist in this small 6-row strength 2 covering array. And what I've done here is I've just shown you how this computation works out. So I'm just going to step through a few of these column projections. And you will notice that for the second one, if you just scan down those columns, you'll see that 1, 1, 1 appears twice. So we know that there are only 5 distinct 3-tuples of the 8 possible. That's where the 5 upon 8 comes from. And if we look at columns 1, 2, and 5, if you scan down those columns, then all of the tuples are unique. So that's where the 6 upon 8 comes from. And if you add them all up, there are 10 3-column projections. That's where you get the 70%. And you could do the same thing for the other example that we had. Okay. All right. So how do we get to combinatorial testing from covering arrays? It's a simple mapping exercise. And so your software could take various forms. It could be a simple function with m arguments. We'll refer to the arguments as inputs. It could be a graphical user interface with controls like checkboxes and combo boxes and so on. It could be a configuration. Configuration may be something like a machine learning library with hyperparameters or the options in the optimizer for a compiler. So how do we use a covering array to derive test cases for those things? Well, here's a mapping. The inputs of the software, the system to be tested, become the columns of the covering array. The levels that we have been talking about can be derived by examining the inputs and constructing equivalence classes. And anyone who has been around test engineers who have some experience or some formal training in testing will hear them talk about equivalence partitioning and boundary value analysis. These are techniques that they use whenever they are faced with continuous inputs or inputs that have a large number of values, so they can partition the inputs, partitioning them into mutually exclusive classes. And so the equivalence classes, the way in which they are partitioned, determine how many levels we have. And then the testing budget ultimately determines the strength. What you may have noticed, as the strength increases, the size of the covering array increases, and so testing budget ultimately determines what strength you will go for. And then the rows of the covering array are the test cases. So the covering array provides a mechanism by way of its rows that you can derive test cases for your testing suite. Okay, so an illustrative example here. And the example I will use is an example that I'll go back to the Mallows, the Dalal and Mallows paper. They used an air-to-ground missile system as an example to work through the paper in Technometrics. If you're interested, you can go to it, but I'll touch on the main thing here. So you can imagine here that the challenge is to validate the software system that controls response during attack maneuvering. And it's real-time software system with 10 sensors that track values for speed, pitch, roll, temperature, the like. Problem here is that the inputs are all continuous, and the moment you see that, you will recognize that this tells you that the input space for the software system is infinitely large. So it's a problem. Exhaustive testing is impossible. But test engineers are not fazed by challenges like this. They know that when you're faced with continuous inputs, you can make the problem more tractable by simply applying that equivalence partitioning mechanism that I mentioned earlier, right? And so let us say that a test engineer faced with this decides that I know what I need to do. I know that my inputs become my columns, and my levels simply will be values from the partitions for each of those continuous inputs. And let us say that I decide that 2 equivalence classes are sufficient. I'll select a value from the equivalence class partition, which is low, the low values, and a value from the partition that has high values. And so we would wind up with a situation like this. This is still quite a challenge, because if you look at this, you will see that the input space, although more tractable, they're still over 1,000 points. And depending on how expensive it is to execute each test case, this could be an extraordinarily expensive task. So the question is, how would a test engineer proceed? So let me begin by saying that there is a naive approach that you could take here. And the approach looks something like this. What if I just said, I know what I'm going to do. I'm just going to make sure that each of these inputs has a high and a low value. And then I'm assured that when testing, I'm not ignoring the high or the low value for any input. The problem here is obvious. If we look at speed and roll, they're missing combinations. And so there could be a fault that precipitates a failure that is due to any of these missing level combinations. And so the test engineer is really not able to assert fitness for use by using a strategy like this, because the engineer doesn't really know what the exposure is. Now, this may seem like an extreme example, but it's actually an example that in the testing community is known as all values testing, right? And so there is the danger of all values testing. You will wind up with a situation where there are combinations of inputs that you are ignoring that could very well be in combinations that have faults associated with them. So this strategy is an approach that I call the naive approach. So the covering array approach says, well, just construct a covering array using the inputs and the levels that we looked at earlier. And so we have a strength 2 covering array example here. And if you look in speed and roll, there are no combinations that are missing. And so the test engineer looking at this can assert that if all of these test cases, right, this is a covering array, remember the rows become test cases, when executed result in success, that is actual and expected behavior agree, then the engineer can assert that if my partitioning scheme is valid, right? If a strength 2 covering array is what I can afford, then I can assert with confidence that there are no faults due to the combination or interaction of 2 inputs. And at any point, as the test engineer is exercising these test cases, the test engineer knows what the coverage is, so the test engineer can assess the risk of stopping early. Okay. By the way, this is an optimal covering array. All right, so let's look at some coverage metrics. So look at that. What is remarkable is for even this 6-row covering array, this 6 test case example, almost 69% of the inputs due to 3-column projections are also covered. And 37% of input combinations due to 4-column projections are covered as well. Okay, so is combinatorial testing effective? Well, the answer, we know the answer to this. Rick Kuhn at NIST and his colleagues have done testing, and they've discovered, the chart tells you for several 5 classes of software systems that they tested, you rarely need more than a strength 5 covering array. And so it is partly because of this reason why there are so many software engineering scholars who believe that combinatorial testing is one of the most important developments in software engineering since 2000. Okay. All right, so there is more though. I gave you a little bit of an overview of, basic overview of covering arrays. In fact, in the real world, you often have constraints between combinations of inputs. And so those constraints are referred to as disallowed combinations or forbidden interactions. And so for combinatorial testing to be useful, we really need to take account of those. And the discrete mathematicians who have been developing the theory of covering arrays have not developed that aspect of their work as well as we would like. So we need something more than the basic definition of covering arrays that I presented earlier. We need an extension. And so I present here what I call a constraint covering array. This is the language that I use. I wrote a chapter in a textbook called Analytic Methods and Systems and Software Testing a few years back. And so this is not universally used term, but it is a definition that encompasses the reality that there are constraints that impose what are valid combinations of inputs in the real world of software testing. And if we're going to develop combinatorial testing as a theory, we need to be able to construct covering arrays that have constraints in the symbol combinations that exist. In another paper that I wrote, I showed how you could extend the T coverage metric that Colin Malles and Disallowed proposed for this new class of covering arrays. And so here's a simple example. Here, if column 1 is 1 and column 3 is 1, that is not allowed. And the covering array example you see here is a constraint covering array that honors that restriction. So there's some takeaways. I'm gonna wrap this up pretty soon here. The cost savings from combinatorial testing can be dramatic. Our binary covering array table sort of demonstrated that. But basic covering arrays are not sufficient. You need more sophisticated ones. Constraint covering arrays, they are variable strength covering arrays, they are more. And the theoretical work has been done more recently, but they exist. I argue that covering arrays address the selection problem. It's a test case. It tells you what test cases to select. And it also provides insight into the quality problem by way of the coverage metric that I mentioned. And they are an effective and efficient tool for deriving test suites. And that's why Rick Kuhn and his colleagues coined the term pseudo-exhaustive testing back in 2006. I get a few questions when I get to this point in presentations I do in covering arrays. How do you construct them? Well, for practitioners, they don't really need to know the mathematics because there are several free and commercially available tools that are available. But invariably, someone insists, well, I want to know the construction algorithms. Well, there are a lot of them. But there are two broad classes, mathematical approaches, algebraic, direct, recursive, there are a number of them, and then there are computational or search-based approaches. And the tools available are tools that use one or the other, or in some instances, the work that I do, I look at hybrid methods where I use both. And so what are the tools? This is taken from the book chapter that I told you earlier. There are a number of them. You can see ACTS, the one at the top, is offered by NIST. It's freely available. There's ATG, which is one of the very early ones, and there are a number of others, right? IPOS, actually, IPO means in parameter order. That's what ACTS is based on. So there are a number of tools. Some are commercial, some are free. So historical aside, this idea of combinatorial testing, although the name is new, goes all the way back to 1985, and you can see how I attribute the unveiling of the history of covering arrays and combinatorial testing there. So that's all I want to say about covering arrays. I want to say a little bit more about what is going to happen in the second part of this presentation. I'm going to set things up for my colleague Ryan, where we're going to look at a set of case studies. I'm going to spend a few minutes setting things up for Ryan. Ryan is going to get right into the nitty-gritty details. He's going to construct them. His is going to be a hands-on presentation where he shows you how these things are constructed. And I'm presenting here perhaps one of the most famous examples that you will see in the combinatorial testing literature, the so-called Tcas problem. And if I know many of you haven't been on a plane for the past year, I certainly haven't. But if you know anything about commercial aviation, you will know that there is this notion of a protection envelope around commercial aircraft, right? Mandated by civil aviation authorities, that allows planes to communicate with each other and know when an aircraft is threatening, by which I mean getting too close to another aircraft. And so you can see that there is an alert that is raised if an aircraft gets into the caution area, a more serious alert if it gets into the warning area, and then we hope it doesn't get to collision. How does this work? There's a computerized system that lives on commercial aircraft, and there are sensors that feed into it. And we want to focus on just the computer unit, the software that runs on this system. And it's a simple piece of software with 12 inputs that track various things, separation between aircraft and the like. And the type of those inputs there are a variety of them. Some are continuous, some are discrete, some are Boolean. And so by now, you know that the strategy is, if I have continuous inputs or even discrete, I may want to apply equivalence partitioning. And because this is a widely studied problem, there is some consensus that a reasonable way of partitioning these inputs is as I've shown here, right? So if you read the literature and you see this example, this is almost always what people will choose. Now, once you get to the stage where you know what the inputs are in your levels, then it's not too difficult to see that a covering array with its 12 inputs, you can see that up separation and down separation have 10 levels. And as you go through them, you'll see that there's one input with 4 levels, one with 3, 2 with 3, a bunch with 2. That the problem now becomes more tractable because we have dealt with the continuous inputs, but exhaustive testing is impossible. Testing aircraft, the Tcas system is expensive. There are almost 500,000 points in the input space. So exhaustive testing is certainly not feasible. So how about a covering array? And so that's what we're going to show you. Ryan will show you what is involved there. The other thing we're going to do is look at a machine learning problem, right? We're going to look at Xgboost. And for those who do not know what Xgboost is, it's a machine learning library that is perhaps one of the most widely used libraries in Kaggle competitions. Kaggle competitions is a popular machine learning competition. It has been around for a few years now. And it turns out that one of the things you have to do when you are using Xgboost is you have a set of hyperparameters that you have to tune. And Ryan and I got really excited when we started looking at Xgboost and said, aha, how do people know that when they set a tuning parameter one level and another tuning parameter another level, that things are working as expected? So some of these hyperparameters are continuous, some are categorical. And so the challenge here to validate the configuration space of Xgboost is a daunting task, right? But again, you can apply equivalence partitioning, and this is one partitioning strategy that we came up with. I've just listed the number of levels rather than the actual levels, but the input space here is still extraordinarily large, and so exhaustive testing is impossible. And so the strategy that Ryan is going to share with you is how you could use combinatorial testing to validate the hyperparameters of a machine learning library. So that's what Ryan is going to focus on, but he's going to focus on one additional thing, a new problem that we are writing a paper on, and how do you validate a project that Ryan and I and others have worked on called the profiler. And he's going to talk about some other things that we wrote about in a recent paper that came out last week, actually. And that is what we term combinatorial testing in practice, right? So that is my first part. I went a little bit more quickly to make up for the lost time. I apologize for the snafu with the screen sharing, but that's what I want to share with you. And we have a few minutes, maybe a few minutes, Tom, where I can take some questions while Ryan is getting ready.
Sure. At this point, there are no questions in the chat. I hope that people will come up with some. We decided to give people a short break. If you want to refill your beverage cup or whatever it is, it's currently 1:46. So why don't we get going at 1:50 Eastern? And in the meantime, please, if you have questions, put them in the chat, and we'll start with some for Joseph. And if there aren't any, we'll just dive right in with Ryan. So we'll see everybody in about 4 minutes.
Okay, thank you.
Looks like there may have been a question that popped up as well.
Okay. Can you unshare me, Ryan?
I see a question there.
Okay, thanks.
Let me unmute Laura. I need to go to the participants.
Do you want me to just say it? I'm busily typing it into the chat.
Then just say it, please, Laura.
Okay. So let's see. We are basically replicating the work that Kun and Okun did on the Tcas system. And one thing that we noticed, we're thinking about how to apply this to our operational testing, right, at IDA.
Okay.
So one thing that we noticed is that once you get to the, can you hear me, by the way?
Yes.
Sure.
Yes.
Okay. Okay. Once you get to the very high T-way coverage criteria,
right,
you're basically generating so many tests that, I think T equals 6, we had 11,000 tests approximately.
Oh.
And so I started to wonder if you essentially get the same kind of coverage just by generating large random input sets of the same size, just because, the number of tests you're doing at that point is so large. So we've actually done a little bit of this. I'm still running these tests, but we did notice that essentially random tests of sets that are the same size as the T-way sets get more or less the same coverage. I think we got one fewer test with each, or sorry, one fewer bug was caught with each test set that we ran, with the random sets as opposed to the covering array sets. And so I'm wondering, but I think there is something to the covering array, because more of the test inputs were like within a set were faulty. And so I'm wondering if anyone has looked into this further, or has thought about ways to sort of supplement the covering array tests to create a more robust set of tests that perform well with respect to random testing. Thank you.
Do you want to go with that, Ryan?
Well, you can go first if you'd like to.
Okay, so thanks for the question, Laura. So this comes up quite a bit, right? The effectiveness of random testing versus covering array-based testing approaches, what we are referring to as combinatorial testing approaches. One of the things that I remind people of is that a covering array approach has an inbuilt mechanism that should be reassuring to test engineers, right? The covering array assures you that for any possible T-column projection, all possible combinations exist. For a random testing generated suite, you don't have that assurance, right? You have non-zero probability that you'll have some missing combinations. So what you have to do when you generate the random test is you have to evaluate it. And if you are building the size test suite that you're talking about, 11,000 test cases, then evaluation of any set of test cases of that size is an intractable problem. Because to measure coverage, right, you have to enumerate all possible T-way projections. And the best you can do is a simulation, actually, right? You're just going to simulate the coverage. But the covering array assures you that all possible combinations exist. So you have that assurance going in that if there are no faults due to when you have completed the testing, that if there are no failures, then the software you can assert that there are no faults due to the combinations that you have selected. So that's what I would offer. Would you add something to that, Ryan?
No, I think that was basically, to me, it's the assurance that that definitely if you're doing the random sampling from the input space, especially with that size, those coverage metrics are going to look good even on some of the, you probably have 2- and 3-way coverage, and it'll look good on the 4- and 5-way. But what happens if you've ended up missing in that 1 or 2% that you've missed? Again, it's a low probability, but in that 1 or 2% that you've missed, happen to have had a fault in there. And that with the covering array, you can guarantee that you've covered all of that.
Right.
With the random testing, you may have just gotten unlucky.
Right. And there's no advantage actually in this instance in constructing in doing a random test. It's not that you can construct the random test case faster than the covering array. So that is why I would argue that you are probably well served to choose the strategy which gives you the assurance that Ryan was just pointing out. Does that help, Laura?
Yes, it does. Yeah, we did notice that some of our tests were not caught with the covering array. And I think it's because of the need to constrain the space initially.
Oh, you had constraints. Okay.
Yeah, when you're constructing basically when you're down selecting the factors that you're going to use, right? I forgot what you called them, but you have to sort of select from each.
Or when you're doing the equivalence partitioning?
Yeah, thank you, the equivalence partitioning.
So you would be using the equivalence partitioning whether you're using the covering array or random testing, right?
Yes, yeah, that's absolutely right. Yeah. I'm wondering if maybe it makes sense to, I've seen cases where people take really large sets of random inputs and then sort of use them, basically a combination of random inputs and some sort of coverage criteria together to create sets that are very good at catching bugs. I'm wondering if you've seen anything like that.
Right, so that's an interesting point, Laura, and I know we have limited time for the questions here, but we can certainly do some questions afterwards, I hope. So one thing you can do with covering arrays is you can just seed the covering array with certain types of test cases that you have some sense are test cases are conditions that you would like to make sure exist in the covering array. And then you can construct the covering array and get the coverage property. So that is sort of similar to what you're saying. So you can always do that. Not all tools allow you to do something like that, though. And so that is a limitation that you may find if you use tools available. In the work that we do, Ryan and I do, for our own internal research, we have the capability of doing that.
But
Okay,
yeah,
thank you. That's very helpful.
I guess I should move on, but yeah, I do want to point out that yes, that is definitely a big issue, is that you have to trust in your equivalence partitioning that you've done a good job, that those values are representative. And that's where we have talked before as well about once you have those equivalence classes, you know, there are times where you can kind of randomly choose in there to try to get some of that stochastic nature. But that's, yeah, that's definitely a big thing, is that choice of the levels. I mean, how many equivalence classes are you looking at for each input? Again, if you get that wrong, then you haven't been able to look at those boundaries and corners in the way that you want to.
And Ryan and I just wrote a paper that's under review, actually, where we do talk about adding the stochastic nature. Well, we have two papers, one that just came out that sort of addresses that, where you can add the stochastic nature over time, right? And you can use what we call a blocking factor. And all of those things may be a way to address what you're talking about, Laura.
Okay, I'm
Okay,
going
thank you
to
so much.
suggest that we get
Sure.
started with part 2.
All right.
Okay.
And we can, Laura, I'm sure we can connect you with Ryan and Joseph for further questions if you have them. And again, I'll remind people that I am monitoring the chat. If you do have any quick clarification questions, I'll interrupt Ryan, but let's get going.
All right, so I think I'm going to be doing this because I'm going to be using my desktop to go back and forth between PowerPoint and Jump. And just to point out here, I'm using Jump because that's what I'm most comfortable with. But basically everything I'm talking about, you can use whatever tool you have available to you. So I'm just going to do a really brief example looking at Tcas, because Joseph had done a nice job setting that up, and it's kind of the classical covering array example. But then, as Joseph had mentioned, there is this Xgboost example and what we're going to call a disallowed combinations profiler. And so both of these were actually situations that came up in Jump. And so our test engineers were faced with trying to test these, and even knowing about combinatorial testing, it was still a non-trivial problem to try to accomplish this. And again, so the Tcas, I mean, Joseph's already set this up, right? We have the protection envelope, and he had set up these different Tcas inputs. Now, I just want to point out a lot of this, the run size in Tcas, if you notice this up and down separation, both of those have 10 levels. Right, so now, if we look at that input space, again, it was still almost 500,000. But now if we think of the strength of the covering array, so again, how many of those combinations, low order combinations, do we want to ensure? Well, if you look at a strength 2, at a minimum, you need 100 runs, 100 test cases because of those two 10 level factors. And likewise for strength 3, that lower bound is 400. And it turns out that actually in Jump, for strength 2, 3, and 4, we can actually hit that lower bound in our construction. Actually, I'd end up to strength 5. Strength 6, that's the best that we've done, around 9,600. But I think let's just move right into Jump, just to show you actually how. So again, if you have Jump Pro available to you, you can find covering arrays under DOE, and it's the special purpose covering array platform. Now, if you're familiar with Jump and the DOE platforms, the general idea is you can add your factors, change the names, change the level settings, everything like that. For convenience, here I've just set up the Tcas factors ahead of time. Right, so for that, the reason for that, I just go to load factors. And if you notice, so there's my Tcas factors and other different level settings. Now here for now, let's just take a look at the strength 2. So again, as I'd mentioned with those 210 levels, the minimum should be 100. So let's just see. I'll say make design. And actually, so that was not even a second. And you can see that the strength 2 I'm not going to go all the way down here, but you can see the number of runs is 100. So which was we hit the lower bound. And so because I asked for strength 2, this should be 100% 2 coverage. But you'll also notice here for the 100 runs, we were still at about 70% of the 3 coverage, right? So depending on your budget constraints, whether or not you want to go up to the strength 3, that starts to depend on how big of a risk am I willing to take to go up to that next, to increase my strength by 1. Now, for something like Tcas for commercial aviation, you're probably not willing to take that chance, but you think of depending on something like statistical software, that's where you have to make some of those decisions. Now, I went back and all I did here is I just changed this strength to 3, right? So again, let's just see on my slide, I had said, I think the lower bound here is 400 because we have those 2 10-level factors and a 4-level factor. And so you see a slight pause, but again, we actually hit the lower bound again. So now with 400 runs, now you'll also notice, so this goes back to that idea as well. As you start filling in more and more runs, you're going to invariably increase the coverage of those higher strengths. So here we can see, so the strength 3 coverage was 100% because that's what I asked for. But if you look at that strength 4, you're almost at 95% of the 4-way combinations. Right, so already you've already hit almost everything in that 4-way space. Again, now this goes back to that idea though. I can't assert that I've hit all 4-way combinations. Right? But now if you think that faults are rare, so the chance of that fault being in those 4-way combinations that you've missed, it's a lot lower of a chance. Now let's just try strength 4 just for fun. Because you see for those ones, I already had the lower bound. Now, if you notice on this one, the lower bound is actually 1200. All right, so I asked Jump to create the design and it got to 1382. And again, now you look, so that 4-way coverage was 100 and our 5-ways at 95%. But now I might say, well, that 1382, can you do any better? All right, and if you notice right underneath here, we have this optimize. So what optimize does is it says, I'm going to take this design, this covering array that I have now, and I'm going to try to reduce the run size. And so you can actually see here, it's pretty quick that I went from 1382 to right now 1225 in about 10 seconds. Right, and I'm not going to let it run all the way through. Sometimes it'll get to the 1200, sometimes it'll take a while. But you can see in that, so I was able to reduce the number of runs by about 170 just by spending that extra 10 seconds. Now, what did I lose by that? My 4 coverage, it's still guaranteed that I have a 4 covering array. So that was going to stay at 100. But now I've lost about 1% in the 5 coverage. And this is where you kind of have to weigh it. Is that extra 1% really worth the extra 170 runs? That depends on your context. So that's all I had in Tcas. That was just to kind of set the stage for some of this further thing. Just, is there any questions before I move on to the next example?
There are none in the chat.
Okay. Okay, so let's move on to just the Xgboost one that Joseph had mentioned earlier. Now I'm just going to open up Boston Housing. So for those of you familiar in the machine learning crowd, this Boston Housing, you've probably seen a lot. But all this has different variables on house and on housing prices, on housing and how it affects the price. Now I'll just mention, so again, if you're a Jump Pro user in Jump Pro 16, we've added an Xgboost add-in. And this is really what got Joseph and I's interest in this. So in this case, I'm actually going to do repeated k-folds, which is something that we have in there. Right, so I'm going to pick all of my regressors. You don't need to worry too much about this. I'm just to kind of set the stage here. And I'm going to try to predict the response. Okay, I'm going to hit OK to go. Now, imagine that you're a test engineer who's been told, well, you have to test this new Xgboost platform. Right, and actually, maybe I'm going to just set this up in the slides a little bit if I can bring them up. Actually, you know what? We're just going to continue on as is. So I want to point out here, when Joseph before was talking about that Oracle problem, deciding if the result actually matches what we expected is very difficult for something like Xgboost, right? So imagine now that the developer in Jump has added a new feature that isn't in some of the other open source libraries, right? Or you see some of these statistics that show up. Imagine as a test engineer, how do you know that these numbers are correct? All right, it's one thing to check whether or not were these plots empty, did Jump crash? If you want to go in and now check, do these numbers make sense? Are these numbers correct? It's a very time-consuming task to go ahead and try to make sure that everything's working. Because on top of that, you can think about things like in this model, right? I might have something like the profiler that shows up. How can I assert that this profiler is working? And even for these statistics, there's also that matter of, do you even trust what was coming out? Right? And oftentimes for the test engineers, so for something like statistical software at Jump, I mean, our test engineers essentially have to go and independently calculate these numbers, right? They're figuring out their own oracle to see, do the results match what I expect? And I'll say what's even worse a lot of times is that if those numbers don't match, then oftentimes you can't go directly to the developer. You actually have to prove to that developer, right? You have to say, I've checked these numbers. This is why I don't think it's correct. It's not really enough to just say, something looks suspicious. And depending on the developer, sometimes it is enough to say, something looks off here. Do you want to take a look? But let me just go back to that Xgboost for a minute here. So just think about how daunting that task was. Right? If you think about Xgboost, think about all of these hyperparameters, right? The max depth subsample. And once you go under these advanced options, maybe at best, you could think about starting a unit test to make sure that each one of these works correctly. But where do you go from there? Right. So oftentimes you might say, well, I'm going to see what happens if I change max depth from 6 to 7. Is everything going to work okay? But when you think about how expensive that oracle problem is, how much time a test engineer has to put into checking that everything's correct, then you also start thinking about, well, how do I even examine the corners? Then it becomes an extremely difficult task. But so let's just take a look here. I'm going to close Boston Housing. So in this case, so all that I've set up, I have 34 columns here again. I set up my factors ahead of time. So you can see under those advanced options, all of those different things that I had. Now in this case, I just took the crude approach. All right. So if you notice for these continuous inputs, part of the problem is with continuous, it's essentially an infinitely large space. And so this is where you have to trust in your equivalence partitioning, right? That I want to be able to reduce that continuous space into discrete categories. And I want to be able to take a representative value from it. So in here, let's just pretend that I just picked two values. I picked a low and a high, and I said that was good enough. Right. And you can see for some things, we have tree method that actually has 6 different levels. The feature selector had 4. Okay. And I think so those are actually the 2 largest. So a 6 and a 4. But again, let's just try a strength 2 and see what happens. And actually we see, so in this case, it actually hit that lower bound again, pretty quick. And I think if I want, I could go back, do the same thing for strength 3. And again, 92, I think we can do better on that. Well, let's just leave it at that for now. So now invariably, so this happens a lot that, you start talking about this equivalence partitioning. How do we determine those number of levels? Actually, let me bring up that covering array again. So let's just look at that strength 2 covering array again. I think I have it in there as well. Okay, so if we think of this, so this was 24 runs where I just treated all of those continuous factors at 2 levels. Okay, now it's not uncommon for somebody to say, well, how come you only did 2 levels, right? Wouldn't something like 3 make a lot more sense, especially if you think of your default values, right? So for some of these, there was a default value in there, and I picked low and high relative to that, right? So maybe it makes sense to add a 3rd level for these continuous ones for that default, right? So that would say, if I don't touch some of these and then start turning the knobs on others, is anything going to happen? And so what this other factors table does, this is now just treating these continuous at 3 different levels. All right, so you see everything that was binary before, for the most part, now has 3 levels, unless it was truly a binary that I couldn't do anything about. But so let's just see. So now I have a lot of 3-level factors, but I still have that 6 and the 4 that were the largest. Now you see, so we actually, and this one, I got a 30 run design. And you'll see, I'm going to stop it here. Let's just say it was 28. I can't remember if I've been able to get smaller or not. But now if you think about when I treated everything as binary, I was able to do it in 24 runs. Now I had really good 3 coverage, but that was also because I was only treating those things at a low and a high. But if you think by upping that number of levels, so changing all of those to 3 levels now, I really didn't take much of a hit on that run size. So instead of 24, now I'm at 28. Right, and even that 3 coverage, the reason I'm taking a hit on that has more to do with because now I have all of these 3-level factors, right, which are already at 27. So 3 to the 3rd is 27. It's going to be hard to hit all of those 3-way combinations. But this is now somewhere where test engineers have to start making that trade-off that, maybe that binary is not good enough. I don't believe, and this goes back to the point that we had earlier in that Q&A, maybe I don't believe that a low and high is good enough. I think I should have an extra value in there. I should have a couple of extra values. And one of the nice things with that is that depending on those factors that are driving the size of that covering array, so in this case, again, it was the 6 and the 4, you may not take much of a hit on your run size. Right? And so that's what we found oftentimes that, there's really oftentimes not that much harm in going up, increasing those number of levels. The other thing that you'll notice, especially when it comes to the binary factors, so adding 2-level factors, you very rarely take much of a hit on the run size by including those. So oftentimes when we're talking to test engineers, we'll say there's something, they say, oh, I don't think that it's going to have any effect. But you know what, there's no harm then in sticking it in your covering array. It's not really going to have any effect on your size, the size of the covering array, but that just in case there was a developer who forgot to check for a flag somewhere, there's kind of no harm in including those in there. So if you think of that from the typical design of experiments, if you told somebody, oh yeah, just add those 5 or 10 factors into your design, no problem. Well, usually your run size is going to go up by so much, you're going to say, there's no way I'm going to do that. For something like a covering array, again, here I had 34 inputs, and even at 3 levels, I was down to just 28. My test suite was only 28 runs. Now, I do want to point something out here, though. So if you think back to Joseph's presentation, he was talking about that idea of disallowed combinations or forbidden edges, right? And for Xgboost, there's actually quite a few. Right, so here I have a constrained covering array, but actually I think I'll just walk you through how to construct it here. Why don't we do that instead? So let's go back to those factors again for Xgboost. So again, I'll just show you one simple one here, but for Xgboost, there may in fact be a lot. But so for instance, the sample type, it only makes sense if booster is equal to Dart. Right, so if that's not the case, then it doesn't make any sense to be looking at sample type. And so at least, so in a lot of those tools that Joseph had outlined, they have ways to specify these disallowed combinations or forbidden edges. So in JUMP, one of the ones that I like to use is what we call this disallowed combinations filter. So again, after you've set up your factors, we have these restrict factor level combinations. And so here I'm going to control select. So I'm going to just pick booster and sample type. And this is because I have my text really large. But what I want to say is that, so if booster is either of those, then sample type doesn't make any sense. So this disallowed says, don't let me use any of these kind of combinations. And so let's see what happens here. So let's take a look at, okay, so we can see when booster is Dart, then we have sample type here. But if we look down at the bottom, so when booster was either the GB linear or GB tree, then there's nothing there for sample type. So this is also going to take a little bit of getting used to, but if you think of if you're familiar with design of experiments, you wouldn't think of seeing a designed experiment with missing values in it. But in here, this actually does make sense, right? You don't really want a placeholder for sample type because you know the sample type isn't relevant when this is GB linear or GB tree. Right. And so there's no harm in all. And so essentially our diagnostics are going to be updated for that as well. And if you also notice in here, this number of runs was actually only 25, right? So we didn't even have really any extra hit. And I think I can even get to 24. Well, I'm just going to hit cancel for now. I think I have constructed it in 24, but you can chain these together, right? So if you use ORs, you can start chaining together a whole bunch of disallowed combinations so that when you're constructing your covering array, it's going to take all of those into account. And just to point out, for something like Xgboost, both cases are actually relevant to, there are times where you want to use the unconstrained test case. So even though sample type is only used if booster equals Dart, imagine whether it's by scripting or whether in the interface, if it allows you to do both. Right, you want to make sure that as a test engineer, you want to make sure that that developer hasn't forgotten to check for a flag or that they've assumed that, oh, there's no way that it could have went down this code path. So in that case, the unconstrained still makes sense, right? So going back to that idea that if testing is is to try to uncover these faults, then you may want that unconstrained test case. Now, further along though, once you have a better sense, once it's a little bit more mature and you feel like, okay, we've covered a lot of those cases, that's when you might want to move into that constrained one. Because I don't want to spend my time, it doesn't make any sense to have those unconstrained. That's when you may want to move on to that. Okay. Let's see, any questions at this point?
None so far.
Okay, so let me just move on to what we like to call analysis of covering arrays. So a natural question that comes up. So covering arrays are great for saying, you know, if everything passes, then we can assert that there's no faults due to these T-way combinations. But now the problem is, so what happens if you actually do uncover a failure, right? So the test engineer is going through. So let's just pretend here I have a response column. We'll just say one is a pass. Again, a very expensive pass typically. Again, that's where they're checking. You may have a really large script checking all of those statistics, checking the graphics, but let's just say everything passed. Except I'm running my tests and then suddenly test 22, there was a failure. So now what are you supposed to do? So the problem is if you take a look at that test 22, well, there's still those 35 inputs, all of those different combinations. So again, this is where, but if you think about these different combinations, so let's just take a look at max depth and subsample of a 3 and 1. So I can already tell you, well, I know that this can't be the cause of the failure because I've seen that combination somewhere else and I didn't have any problems. Right. And so in JMP, we have this, what we call the analysis tool. So that actually goes through and it says, I'm going to throw out any combinations that I've seen elsewhere that passed because I know that those can't cause the failure. And so you see, so what the test engineer can now do, this tells the test engineer, this would be to where to start to look. So maybe try that call sample by tree when it's set to 1, tree method exact. Try the tree method exact, booster is GB tree. Or you check this third one. And so that's the thing with covering arrays, because they're so cost efficient. When you do observe a failure, the fault localization problem, by which I mean, what was that combination that actually caused that? That can be very problematic, right? And that's why in JMP, this is one of the tools that we built in there to try to make the test engineer's life easier. To say, well, this is where you can go start to look. And so what was interesting is that what we've also found, so another paper that Joseph and I have has to do with weighting some of these, because oftentimes if you give a test engineer a list, you know, you'll say, these are the 8 different combinations that this analysis was. You'd be shocked at how often they would say, they'd look at that and they can say, oh, I know it's this one, or that's where they're going to go look first. right? So that's the other nice thing with this analysis, is that you can even actually take that into account. You can say, well, if you want to supply me some weights as to what you think is more likely ahead of time, you can take that into account to give you a ranking. Now I'll just point out, so let's say if there were actually 2 failures. Right, so let's see what's going to happen there. Right, so in this case, so it won't always be like this. It just happened here though. If you look, this booster and feature selector actually occurs in both rows that had a failure. So if I'm a test engineer, well, what's more likely the case? Is it that I had one single clause that would explain both of those? Or do I have this one on this row and maybe this one on another row? Well, in a well-controlled system, so I mean, this is also a case where if I'm using covering arrays, I hope that I'm in a case where I'm not hoping to find too many faults, right? So I'll say you also won't be shocked if you've never done combinatorial testing and you throw it at a system for the first time. You may actually find a whole bunch of failures, right? Because there's a lot of those corners that you've never looked in before. But once it's well controlled, then this would immediately be the first place that you would go to look, right? So instead of having to run all those different combinations, you can say, well, let me take a look. If I set booster to GB tree and feature selector to thrifty, do I get that failure right away? Right, so that's one of those things. That's what we call analysis in JUMP. And so that anytime that you create a covering array within JUMP, it's going to come out with that analysis script. And actually, even if you're bringing in your own covering array, in the covering array platform, we have something called load design. You can load that and then just output it, and then that script will be there. Now the last example, so I know I've got about 10 minutes left here. Just something I'm kind of excited about. So this is what we're going to call the disallowed combinations profiler. Again, I have it in the slides. So if you look at the slide deck after, it's in there. But a disallowed combination, it's actually that same idea we were just talking about in the covering array for the Xgboost. Right, and in here, I have a disallowed combination from a designed experiment. So this isn't a covering array. So this is a disallowed combination that if you go under your DOE menu and custom design, it's not uncommon that you have a disallowed combination. Now in here, when I created this design, I told JUMP that if X1 was at the level L1, then X2 can't be in between these two values. So here X2 and X3 are continuous and X1 is a 2-level categorical. Now in previous versions of JUMP, if you ever use the prediction profiler, again, that's one of my favorite places to go. If there was a disallowed combination, then the prediction profiler would have the line here. It didn't know, basically the prediction profiler completely ignored the disallowed combinations. And so obviously that's not desirable because you can't go there. If your X1 is at level L1, then you can't go in this point at this point here. Now, if you're at L2, then you should be able to go in this entire area. Now, you notice as I'm dragging this along in X2, you can see what's happening here to X1. Sometimes it's there, sometimes it's not. So you can start to imagine this is actually a really difficult problem to try to profile this. And in particular, because you don't know what the form of those disallowed combinations are going to be. So here I've just been showing simple disallowed combinations. I have examples though where the disallowed combination can be a map shape, right? You can say I only want my points to occur over the map of North Carolina, right? And what makes this actually worse too, so you can imagine what often happens in these disallowed combinations case is if you tell the profiler, maximize desirability, find me where you predict the largest response is going to be, it wasn't uncommon that it would actually go to a region that was disallowed. Right. Well, the problem is that the whole reason it's disallowed is because we can't get any points from there. All right, so that doesn't do a whole lot of good to a practitioner. So part of the problem with this now, though, is that we've heard complaints from customers, right? But we don't really have that many good sample data sets. right? So if you think of something like Xgboost, you go to the literature, right? There's lots of different examples. You can start to then, I had the Boston housing, but you can start to go through all the different literature, find different things. But here, we don't really have that much in the way of data sets. And the other problem is, if you think of this from JMP's perspective, from the test engineer's perspective, there's a lot of different ways that people are going to be loading data into fit model and trying to profile it. Right. So it's not enough just to look at that simple example. We have to think about how best to go about exploring different types of data sets. And so really the solution that we came up with here, so we were working with the test engineer on this, is that, so incorporate the different data sets. So data set creation or data set generation is going to be part of the covering array process. And so by that, I mean, when you think of these, the factors that we usually had, so for Xgboost, I mean, it seemed pretty straightforward, that configuration, right? We had the different hyperparameters. How are we going to set those? Now I kind of waved my hand because I just used Boston housing. So it'd be possible that another one of the inputs or the factors that I could have had to the covering array was the different data set. Right. And now again here, because we don't really have great data sets, we came up with a solution that would generate the, let's see, that would generate the data set using a covering array. So this would say, give me a mix of discrete numeric, continuous, categorical factors, so that now we can try to make sure that we're getting a good mix of different data set types for the purposes of testing this disallowed combinations profiler. And so if you see here, actually, maybe I'll just load it directly up into the covering array platform. It will be easier to see. So let's load those factors. So in here, because usually these disallowed combinations are actually coming from a DOE platform. So here we just defined these X's to be, how am I going to tell the custom design platform to generate the data? However, there's nothing stopping you. These X's could be, how many factors to generate? How am I going to generate them? Are they going to be a random uniform, a random normal? Do I want to imply some kind of covariance structure? Anything you could think of, you'd want to put in here. Right? And so you can see number of responses. What's the goal? The goal of the response, right? And you can see building in different kinds of constraints for those disallowed combinations, different types of models, run size. But also as part of this is where you can have this reset factor settings, sensitivity, maximize and remember. So some of these actually have to do with the profiler itself. So in this case, right, if we look at what comes out, so here's my covering array. So we actually had 13 runs here. Right, so a single run in here would tell me, how do I generate the data set? Right, so in this one, it would say, my first factor is going to be a 3-level discrete numeric, the same for X2, X3, then a 3-level categorical. And as well, it's going to tell me, well, what do I want to look at when I get into that profiler? What are some different steps to take once I'm looking at the profiler? Now, the nice thing is, I know I'm running short of time, but just to show you what would happen here, right? So this would be one run of that test suite, right? So the nice thing too about using something like JMP, if you look at that DOE dialog, if you're really good at scripting, this would tell you how to generate your X1 and X2 and everything like that, right? It would tell you, how am I going to go about generating X1? That would be a 3-level categorical, 3-level discrete numeric, etc. So this would be one run from that covering array. And you also notice, so here there was this test least squares. So this would also be defined by the covering array to say, what am I going to do in the profiler to check if this is working? So I think this was something really new to us, that idea of data set creation as part of the covering array process. And really it was a necessity here because we didn't really have good data sets, and we wanted to make sure we were covering as many possibilities as we could. Anyway, I think that's probably a good place. It looks like I'm at 2 minutes, so I think that's probably a good place to stop there.